This is my program. My name is Janis Griffin, and I'm going to give you a 12-step tuning program. Just a little bit about myself before we get started. I've been a DBA going on for over 25 years now. I started out with Oracle version 3. Some people say I'm older than dirt. But actually, I actually took on MySQL years ago, early 2000, version 3 of MySQL. Running 911 networks. Our soft switches actually had databases on them, and it was MySQL, so it's near and dear to my heart. I've been at SolarWinds for 10 years, going on 10 years, working with our customers, our prospective customers, looking at their databases, giving them some ideas of what's going on inside. And a lot of times we get to that place where there's a inefficient query, and they go, well, where's the magic button? How do I tune it? And so that's the reason for this presentation. We're going to talk about challenges of tuning, because let's face it, a lot of times tuning is just trying to find that one SQL that's going to give you the biggest bang for the buck. And then we're also going to use a technique that I actually have used for many years now, response time analysis, or we've actually retermed it to be wait time analysis. And then we're going to jump right into the 12 steps. Now, I've got a couple of case studies too, so hopefully if we have enough time, we'll get to those. Okay, so let's get started. And please, if you have questions, please, I don't mind if you raise your hand and slow me down. It is a 50-minute session, though, and getting through 12 steps, that's less than a few minutes per step. So, but let's face it, SQL tuning is hard. It's just plain hard. You get thousands or millions of SQL statements running in the database. There's no cookie-cutter approach on how to tune. Each SQL statement usually requires you to, look at it, do some different things. You need to have to know the technical aspect of it, how MySQL is going to go get that data off disk. You need to understand the explain plan. You need to, I think it's important you need to know the business aspect of it. Years ago, I worked for a turkey plant, if you will. And every month end, I was responsible for their database. And every month end, they would just scream, it's a database. There's something wrong with the database. And we found this accounting clerk who's running all these reports. Horrendous reports. Some of them were taking 8 hours and just drug down the system. And so we asked her what she was doing, who was using them. And she was filing them in a filing cabinet, and nobody was looking at them. That was the quickest way to tune that situation, was just to shut those reports off. It's just a funny story, because nobody could believe that she had been doing this every month and causing everybody else pain. Low priority in some companies. A lot of people, how many think they can just throw hardware at databases? The thing is, it might buy you time, but it's an expensive solution. Because inefficient queries, as the data grows, as more people use that data, it's just going to consume all the resources it can get. So your biggest bang for the buck is to tune those queries. So we're going to go through rapid fire 12 steps that can help you take care of the problem. Now, I've given this speech before, and people expect this to be the magic sauce. And it is. You can look at it as a reference, but it's not an end-all, be-all tuning class just because it's 50 minutes. If I could transfer or do a brain transfer of all I know about tuning in 50 minutes, I'd be doing good. But these steps will help you at least get a good start. So step number 1, find which SQL to tune. And I've used all these methods before. The first one's really easy. If you've got a user complaining, or maybe you see a batch job running longer and longer, well, you go about seeing what they're running and work on their queries that they're running and watch what they're doing. That one's pretty easy. But if you want to do holistically tune, more holistic tuning, especially if you have a lot of instances that you're monitoring, just out of curiosity, how many people are DBAs here? Okay, developers? Okay, we got a few. How about management or some? Okay, fine. We got one. Okay. Do about anything is my Twitter tag, because I've always done a lot of different things. But the thing is, when you are trying to find which SQL to tune, a lot of times well, let me ask another question. Have you ever tuned something and nobody notices? I have. And oftentimes, if you've done that, you're working on the wrong things. So if you want to more holistically tune, I always like to look at rows examined versus rows sent. Because if you can find the query that's using and doing the most I/O, that's the slowest component on your computer. and you can reduce the rows examined. You're going to speed that query up, and you're actually going to speed up the full processing model there. If you're looking, you can look at CPU. If you can trace and find a thread that's using a lot of CPU, you can start looking at that and tuning that query. But the one that I like to use the most is looking at highest wait times. That's what our product does. I'm not talking about our product in this, but I've used this technique for the last, since early 90s, and I can guarantee you it's the best way to find the queries that are causing your end users the most problem. Now with MySQL, you can get this information out of the performance schema and the information schema. And what MySQL and a lot of the other relational databases have done is they've instrumented themselves to not only record the total time a SQL takes in the database, but it actually breaks it down into little steps, little discrete steps. And as a SQL request goes in, it records the time of those steps and the resources used up or waited on of each step. Now, if you think about it, if you pull that information, store that off in a table, you can quickly see which SQLs your end users are waiting on and the most on. And not only that, you have some great clues of how to tune, because you know which resource to go after to try to reduce the time spent on it. Like I said, you can get this information out of performance schema. How many people use performance schema today? We got a couple. Okay, good, great. And it used to be foreboding to actually look at performance schema because a lot of people had problems because it was a performance hit. Well, in 5.6 and above, they've actually improved the performance of accessing performance schema. And not only that, it's now, if you download Oracle's binaries, it's now on by default. It also defaults to the storage engine, defaults to NODB, which is a transactional model. So then you get all the blocking, locking, all that good stuff at the transaction level. How many people are on earlier versions in 5.5? One, okay. What version? 5.5. Okay. How about 5.6? Okay, 5.7? We got some on 5.7, okay. Well, when they came out with 5.7, what they did is they've added and improved the footprint. They recently reduced the footprint and the overhead much better. Not only that, they added new tables to the performance schema. There's 1,005 instruments now in 5.710. So if you can upgrade, it'd be better to upgrade to that to get this good information. There's more information about transactions, metadata lock, memory usage, and that type of thing, so you get all that. And not only that, if you, again, download Oracle binaries, what will happen is they've installed now a SysSchema that kind of looks like Oracle, the $X tables and the $V tables. So if you're any old Oracle DBAs here, yeah. So if you're looking for that, that would be the thing to go look at. Problems with the performance schema, very detailed. They keep the timing at picoseconds. So what you'll see with the SysSchema, it rolls it up and makes the dates a little more easy to work with. If you wanted to use wait time analysis, and I didn't list out all the tables in the performance schema, but these would be the tables you'd go get. I'm just going to go through them. And in fact, these are not even the all the columns as well. But as you can see here, the one with the little stars are actually in the informant schema. So from the informant schema, I can get the process list. I can join that into the threads table in the performance schema. And notice what I can get. I get user, host, database, command, time, state. I can get it, know what's instrumented or not. And then I can join that into events, waits. That's giving me my wait event. And then I can actually join it into event statements to get my SQL text, my rows examined, rows sent, all that good information. And then if you go back to the information schema, you can get that good transaction data at the NODB level. So you get the transaction thread, the tables, any locking, blocking going on. You can actually see the blockers and the waiters with that. This is a base query. Now, you can read that back there, right? I'm gonna zoom in. This is why I've got Zoom. I hope I don't make you dizzy. But this would be the base query if you wanted to create your own tool. And notice I'm just inserting it into, I call my table WTA data. And I'm collecting the current timestamp, the user, the host, the state, the current SQL text, the command, the wait event ID, the wait operation. I'm getting the digest. I'm actually getting rows examined, rows, and all that good information as well. I'm joining that. I get that from threads. I join that with events, waits, current. And I join that with a session connection adder just to tell if it's a program or a background process, that type of thing. And then I go to my transaction tables in the InnoDB. Notice my where clause. I'm looking for where it's instrumented equals yes. And I'm not looking at myself. Oh, sorry, I hit my mic. And where the process list command is not equal to sleep. I only want active processes because they're sitting there idle. You don't care about what they were doing. They're idle now. It's not rocket science to do this. You create that, you run that query, and you run it at some interval. Like I said, our tool does it every second. And it actually puts it in a table. And you can go back then and run this query. And I just actually did this last night. I actually sat out there and had this run for about 5 minutes, just every second, that insert. And then I went back and I ran this query. I'm selecting SQL text, my wait operation, my time in seconds. Because I'm doing it every 1 second, all I have to do is sum up the records I got, right? And then I actually join it again into the table and get total time, so count all the records for that. And then I group by each wait operation. So my output here, as you can see, you've got my queries that were running at the time. And I had a little load on a DVD rental database going, and so most of it is related to rental. But you can see what the wait operations were, and by ordering it by the most time spent, you can see that I had one query that actually had spent 23 minutes in the database, and within that 5 minutes, with every active session running that. Okay, so that's how you kind of accumulate that total wait time. If you've got that many sessions running it, and 23 minutes encountered within 5 minutes, you've got a busy system. You can see that by breaking down what it did while I was doing it, this was this little select if null film rental into, and it was doing something, but you can see that it spent 39 seconds on a read and, well, almost 22 minutes on fetching. So it's doing a lot of I.O. In fact, if you looked at the wait, it would be SQL handler, I think, I.O. SQL handler. Meaning the wait event that it's just doing a disk into memory read. But right there, within 5 minutes, I know I don't want to focus on those top two. There were 2 seconds in the database. If I'm going to tune, I'm going to focus on the last two. Benefits of response time analysis or wait time analytics, whatever words you want to use. This is just a quick graph of showing you my top 8 SQLs within a database. And you can see my student billing one, it spent 100% of its time, over 20 hours, in this 1 hour with every active session running it on sending data. So what that means is it's probably reading an index or reading a lot of data from disk. My third one there actually spent 16 hours in the database in this 1 hour waiting for a metadata lock. So now I can go to the InnoDB tables and with my query, and I can actually see, okay, this one was waiting, who was doing the blocking. So it's very granular, very great information that you get. Like I said, these wait events and operations are pretty well documented out there in the community. And you've got solutions to each one of them. So if you find the SQL and actually see the resource they're waiting on, then you've got a great clue on how to tune it. This is just another example of the blocking issue where I got one SPID there. If you can see, he caused about 4 minutes there of blocking. And he actually, caused these guys to block as well. They all waited 10 seconds, but they blocked others. And you actually can get up the whole tree. You can see what the blocker was running while he was blocking, and what the waiter was, actually I should have shown that, was trying to run. So they were all trying to update a table called stock. And the first one was pretty slow doing it. Okay, so we found the SQL. We've got some clues on how we're going to tune it. Let's go get some baselines. Because as I tune, what I like to do is get some baseline metrics to compare against as I tune. I mean, how do you know if you tuned it if you don't, you gather those metrics? So what I usually get is, how long on average it takes now to run. And I also kind of set in my brain what's acceptable, or what do I want to tune to. If you don't get that up front, I'll tell you, so you'll drive yourself crazy. When I first started tuning, I thought I had to tune to the nth degree, and I drove myself nuts. There's a point you can stop tuning. And so figure that out in your brain, talk to users what's acceptable for this query to run. But then I always grab rows examined and rows sent, because I hope the rows examined come down for my result set. And I'll talk about that more later. And then, of course, you gather your thread or wait states. And like I said, there's solutions to any one of these. What I often do when I have a lot of wait states in one query, I'll work with the one that's spending on the most. And if you tune that, sometimes some of the others will disappear. Not all the time, but sometimes. Okay, so here's our baseline metrics. And you can see this one student billing that was spending 20 hours in that 1 hour. Was running on average about 5 seconds. It got a little better probably because it was in cache more. But as you can see here, 5.4 seconds are my metrics there for average executions. It did about 13,266 in the 7 to 8 a.m. time frame. Look at my rows affected. I don't know if you can really read that, but it's 191,000 in some. Look at my rows examined, 1 point round up 3 billion. That tells me that it's probably way too much data, reading way too much data for its result set. Okay, so we got our baselines. Let's go get the execution plan. MySQL gives you many ways to get this. You can do an explain, just in stream, and it'll give you that. MySQL is unique in that it doesn't cache the plans that it's using. So you actually have to use explain to get that. You can do explain extended. That's the one I like. Explain with the format of JSON. And if you have 5.6.3 and above, you can actually use tracing. And I'm going to go through each one of these, but I just wanted to touch on them. The thing here with our student billing query, and this is one of our case studies that I'm going to go through. Basically, this came in from a customer. And it's a 3-table join, as you can see. And I'm selecting first name, last name, and sign-up date from student and registration. Joining on registration with student ID. And then I actually go get the class and join registration to class on class ID. And the business reason for this query when it came into us was basically, it was a university. And really, they were trying to bill their students for the classes that they'd signed up for. And I changed a little bit. I put SQL tuning to make it more interesting. But they were passing the class name and into a variable and actually running this. And it was so slow. And the reason why is the registration table was a historical table. They never deleted from it. If the student dropped or canceled the class, they just marked the canceled flag to Y. So we're looking for active only. And so as you read the execution plan, you can see we've got a select type of simple. Notice I used aliases here. And this is one thing I don't like about MySQL. It doesn't bring down the tables if you use aliases. So if you have maybe a 10, 20 table join, and you're using aliases, it's very hard to read. So my tip is, if you don't have to use aliases, sometimes you have to, but if you don't have to, don't use them. But these are simple enough. My S, it first went into student. It did a full table scan. Read 8,700 and some rows, and then basically did nested loops into registration. Looked at its primary key, is using its primary key, referenced the student ID, and then it did nested loops into class, doing an equal reference using the primary key of class ID. So that's how you kind of read execution plans. If you haven't, Python has this great cheat sheet. It's kind of dated here, but I've got the link here. If you look at my slides, you can actually download it. What's nice about this, it explains all the columns in the explain plan, it actually gives you the data access points in the type field. And you can see it's listed by most efficient to least efficient. And my top one is a system access, where just looking at a system value. The bottom one is a full table scan. So you can kind of see what all those mean. And same with the extra column. That's what I like, because sometimes I forget what can be in the extra column. And the extra column will show you file sorts, temporary table creations, all that good stuff. So just kind of a neat poster there. This is kind of my go-to explain plan is the extended. And the reason why I like this is because it shows how the optimizer is going to transform the query. And you basically, how you do that is you just do explain extended, give it your SQL statement. Notice this time I didn't use the aliases, so you can see that it came down with the tables. And then right after that, you do show warning, and that \G, capital G, will actually give you what the optimizer is transforming that query to. And I always like to review that, looking for, well, did I, write it good enough? What is it doing? So you can see, it actually put in the database name, the table name in front of all the columns. It actually put in some parens. It's actually decided it's going to cache a variable and use that. So you can kind of get, I think it helps you write better queries. Here's explain format equal JSON if you like that. Format, it's kind of like XML, I guess, if you want to look at it. You just put format equal JSON. And then it just, and I use the \G again so it printed out nicely. And as you can see, it'll list, how it's going to go, how many rows, what it filtered. The thing I kind of like about the JSON is it does show used key parts, and you can kind of quickly see that. So in my registration, even though it's a composite key, it didn't use the whole key. It only used the first part of it. So that's kind of an important fact to know. If you have 5.6.3 or 5.6.3 and above, optimizer tracing is another option. Now, the way that works, anybody use this? Just curious? Okay. You set optimizer underscore trace equal, and then in quotes, enabled equals on, and then you just run your query. Okay? And then to go see the output, you have to look in this information schema optimizer trace table, because it'll stuff all the results in there. Okay? And when it does that, it will give you every permutation the optimizer went to find the lowest cost plan. So it's good, because if for some reason you've got this plan and you can't figure out why the optimizer keeps doing this, you can get in here and see all of the other choices it had, and it's going to choose the one with the lowest cost, and it might help you understand why it's thinking that's low cost. Problem is, the default of that table is only 16K in memory. So even with 3-table join, I blew it. And you can see this error here. It said missing bytes beyond max mem size. I have 8K that it's insufficient of. So you can fix that. I just want you to notice here, this is how you set it off. You set optimizer underscore trace, and then in ticks, enabled equals off. But if you come over here, you can, like I said, it's stored in information optimizer schema. You can set optimizer trace max mem size. I just set it to 1,000,000. The other way you can do it is you can set optimizer trace features, and then in ticks greedy underscore search equals off, and that won't be as verbose. It won't show you all the permutations. So it's just some tools that I didn't know if they're out there, so that I like to show. The thing I like about trace is it actually will point out the cost. So you can see it gives me the student, the scan, the cost it ranked at 161, registration was 225, and then finally the last step was 10. So it kind of gives you that. And you can go through all of the different join methods that it'll choose and all the different access paths that it tries, and you'll see that in the trace. Finally, my favorite way to look at execution plans is MySQL Workbench. And what I like about that is it actually, it's kind of a lazy way to do it, but you can see the high cost real quick. See that big red square? I was like, oh, okay. I can figure that out. That's probably not a good thing. And it'll come and tell you some information like, you're doing a full table scan. It could be very high if that table is very large. And, then again, it tells you possible keys. It won't tell you, the thing it doesn't do is tell you what part of the key it used. I don't think. Don't hold me to that. Okay, we got the execution plan. Now what do we do with it? Well, what I like to do, and we kind of alluded to it here, is you find the expensive steps. And you look at them. You look at I/O costs. I always, like I said, rows examined, rows sent. Look for full table or clustered index scans. Know your predicates. Filtering predicates. When are they filtered? Make sure you're not doing any implicit conversions. MySQL does do that on the fly for you, but it takes CPU cycles. And typically relational databases aren't CPU intensive. So if you've got CPU intensive databases, I can tell you one thing right now: you're probably doing some converting, some scientific stuff, or you're just reading far too much data, and it's just thrashing memory. And then that, of course, gets pushed out to disk, and then of course you have I/O problems as well. If you have lots of temporary tables and file sorts, they can be a problem because it's just extra overhead. I just ran this little query with this data, and I thought it'd be kind of interesting to see when the students are signing up for classes. So I just did a selected from sign up date, got the class name and the number of students, and because I have to group by there, and I have to order it because I want to see my top day for signing up. I encounter a temp table and a file sort. Now you can fix some of this by putting indexes if you can. It doesn't always work, but if you can and you're referencing the same table in the order by clause, you put an index on it, you can avoid some sorts that way. So it's just kind of a technique you can look at and use. Okay, so once we find those expensive steps, we got to evaluate what they are. And in our case, it was actually student because we were doing a full table scan. So what you need to know is it really a table? Is it a view? You're going to have to tune the view. Or maybe you can avoid the view and go directly at the table. Get the sizes. MySQL has this nice little command line, MySQL show. And you can do, it's a hyphen status. And you can either pass the database or the database in table or the database in column, and it gets more granular as you go. And it'll give you quickly what the optimizer thinks the number of rows are. So I can't stress this enough. You want to know what the optimizer knows. And if you don't know that, you're not going to be doing a very good job of tuning. So what I see from here is my student actually has 9,489 records. Registration has 80,494. Class has 1,000. I can also see my data length and any index links there as well. Examine the columns in your where clause. There are your filtering predicates. And what's neat about that, you need to know the cardinality of them, how selective they are. And if you can combine them in an index and all that type of thing. And we're going to get more into that. But review them, actually review what your select columns are. Please don't select star. Select specific columns because you're just feeding memory or eating memory. Okay, so we got the table information. Let's look at the indexes, keys, and constraints. And again, it's very important if you've got a multi-column key to know which is left leading, because MySQL, if you don't reference the left leading portion of a multi-column or composite key, it will not use that index. It'll turn it off. So it's not like Oracle where you can put a function index or anything like that around it. So or if you're missing it, it won't do an index skip scan, which isn't very good anyway. But so know that. And if your left leading column, know its selectivity most important. You want it to be the most selective in the rest of the columns that you're getting. Okay. Other things. Make sure the optimizer can use the index. Like I said, functions around index columns will turn off the index for MySQL. It won't use it. Implicit conversions can have the same effect sometimes. Not as much in MySQL as other database types, but I'm always aware of implicit conversions just because I don't want the CPU overhead. If you don't do it, trust me, the machine will do it for you. And then also existing keys. Know the existing keys and constraints. How many people here avoid keys? You know, putting foreign keys on tables? Nobody? Oh, you do, okay. Can I ask you a reason why? I don't mean to put you on the spot. A lot of people, and the reason why I ask that, because I've seen, it's been, lately anyway, in some of the other talks that I've given, people avoid them because they're afraid they're going to take the hit on inserts and updates, because you have to maintain that index. But if your goal is to actually get that data back to the application, as opposed to storing it, the keys and constraints give the optimizer more information. And so it just makes for a better execution plan. One thing you can do is just show indexes from your table name, and it'll come back and tell you the index and keys. And you get, for class, we got a primary key, and what's supporting it is this one index called PK class. And you can see the cardinality there. Cardinality of 1,000, I've got 1,000 records. That's very selective, right? It's a unique key. So that's kind of a neat way to find that out. Like I said, run an ERD. It's easy enough to do in MySQL Workbench to just take the tables in your query and draw it, to know the relationships, the indexes, and everything else. And as you can see here, I don't have any relationships. I have registration with the primary key on student, class, and sign-up date. I have a student table with the primary key on student ID, and I have a class table with primary key on class, and I don't have any relationships. What I had done here is this actually was an Oracle database that came in for real. I mean, the customer was running in a university, like I said, and it was an Oracle database, and I thought I needed a case study, so I thought, well, I'll just port this over and see if I can make it do the same thing. And so when I put it over here, I forgot to put the constraints on. So anyway, but as you can see here, you can actually see all your indexes just by doing that show indexes from registration. Okay, so let's review. We actually found the SQL using wait time analysis, and we got a good idea of what resources it's using. We actually went and got our baseline metrics, got our execution plan, reviewed the execution plan. We looked at the tables that are most expensive in those steps. And then basically, we looked at the indexes and all that. Now we're going to go understand the selectivity. And what I mean by that is have you ever wondered how some of these databases come up with their plans? They look at the selectivity and the cardinality of the columns in the table, and they find a driving table. And that's what you need to do if you want to speed up a query, is find the driving table. And how you do that is you look at the number of rows being examined at each step, and you evaluate that with the result sets coming back. And if you're reading millions and millions of rows to only get back one or two to the application, then you've got a very inefficient query. And like I said, I/O is your slowest component on a computer, so if you can fix that, you've really tuned it. So how do you find the driving table? And this is a technique I've used, and here I'm just going to go through this case study again in case you didn't get it. This was coming from a university. We're looking for billing students, and in my case, we're actually looking for just specifically SQL tuning. And we're looking where the sign-up date was yesterday, if you will, and where canceled equals no because we wanted only active records. You can see my baselines here. This thing was running 5.5 seconds in this hour. 13,000 executions, around that all the time. Look at my rows exent was 173 in this hour, 1,000. Again, about 1.3 billion rows examined. Oops, sorry. Well, how I find the driving tables, basically I use a technique called SQL diagramming. I don't know if anybody do that. Query diagramming or anything? Okay. Well, if you want to know more about it, there's a great book out there, and I don't know this man, but it is a good read. and it'll tell you all about SQL diagramming, and it'll tell you, it's a good reference for tuning in general. But anyway, what SQL diagramming is, it's having you draw out your tables in your query in an upside down tree. And so what you're doing is you're taking your detailed tables, and so in my case, I've got registration as my detail table, and you draw these links or arrows out to the lookup tables or master tables, okay? So we had 3 tables in our query, one detailed registration with a lookup into student and a lookup into class, okay? Everybody with me? These numbers on side of the arrows basically are the join criteria. What we're saying is for every one student, there's probably about 5 records on average in registration. And you can figure that out just by selecting average of the count, do a subquery, select the student, the number of records, and then find the average. And then we're also saying for every one class, there's probably about 30 records, because there's 30 people in a class. That's my data. The university had a little more, but because their classes were a little larger. But what we are getting at here is for any one student or any one class, I should never have to join more than 150 records. So in your joining of things, and you're seeing you're joining lots of records, then maybe you're missing an index. Typically in the join fields or join columns, if you index them, make sure all your join columns are indexed and MySQL can use it, it's going to do the right thing. The more interesting data are these right here, the filtering criteria. So we had 2 filters in our query. One was on registration, where we were looking up where sign-up date equals yesterday, if you will, and our registration canceled equals in. Out of that filter, there would be 4,228 records coming back out of 79,000, almost 80,000 records. So if you get the ratio to that, about 5% of registration is going to be read with that filter, right? The other filter was on SQL tuning, where we had 2 records being returned, probably because of different levels of that class, out of 1,000, and 0.2% of that table is going to be read. So which filter is more selective? Class, right? It's 0.2% of that's going to be read, as opposed to 4,000 or 5,000 records. So we want to drive this table by class. Now you notice we aren't driving it by class. We basically are driving it by student. So we really want to turn this picture around. We're going to flip it. Okay, so how are we going to do that? Well, we're going to go see if there's an index on name, because that's our filter on class, so that's how we're going to drive it. So step number 8 is now we're ready. We have enough information to tune that query. We're going to find the driving tables. We're going to try to make it do and use that driving table. Again, look at seeks versus scans, and just try to avoid any file sorts and temp tables. Well, remember I had no relationship, so let's go fix that first. So I just add my foreign key on registration to reference student ID and student, and I added a foreign key on registration to class on class ID. And then you can actually go run this query here to actually quickly see that you've got those foreign keys. And it's just select table name, column name, constraint name, and from this key column usage out of the information schema. And it's going to show you here. Notice I didn't name them. MySQL actually just gives them that name there. Okay, any change by doing that? Well, I didn't. I got my baseline metrics, and I made it worse. I mean, see that big red bar? Adding those keys made it much worse. I was like, really? Why? I thought, telling the optimizer it had foreign keys would help. But it didn't. It actually spiked up. In fact, it's now up. It's now running 15 seconds on average as opposed to 5. So no, I didn't tune it. Well, why not? So let's go back and look at the execution plan. Well, it didn't change the plan at all. We're still driving it by student. we're still, using, in registration, we're still using the primary key. It's not using the class ID index that it put on there because of a foreign key, which I thought it might, but it won't. And so the reason why it took longer, too, is because I'm adding data at the same time. So we had much more data at this time, so it was slowing it down just by data growth. So let's go ahead and try to drive the table and see if that fixes it. So we add the index on class name. I just called it class NM. And you can see it just really improved it. Now we're going to class first, using my class name index. I get 2 rows. Go to registration, I get 38 rows. And then finally, I go to student. Okay, the thing that's neat about this now is I can come up here and I can see used parts here, of it. And it's using, what am I showing here? Well, I'm just using that. It's using class name. So I sped it up. So we look and see the monitoring. What do we do to it? Yeah, we sped it up considerably. As you can see here, it's now 72 milliseconds from that 5 seconds on average. Well, then it went to 15 seconds. Look at my executions. Went through the roof. Before it was 100 and some per hour. Now it's 434,000 per hour. Look at my rows examined. 12 million instead of 1.3 billion. Okay, so you can really see, the impact when you actually use this technique. Step number 9. Maybe I'm not done yet. Let's adjust the index. MySQL gives you many different ways to use indexes, and one is you can make a covering index. Anybody know what a covering index is? You want to?
Yeah, you retrieve the entire result set from the index and you don't have to go to the table.
Yeah. Yeah, you don't have that extra I/O. Using an index, you have to do usually at least 2 I/Os, unless you make it covering where it can get all of its data out of the index. Then you reduce the I/O on it, and so it's a great technique. So we could add a covering index, and all I did was go to the query and the select clauses and the where clauses, got all the columns related to registration, and put it in an index. The other way you can do it, and this is kind of an interesting way, especially if you've got a lot of text fields, and with NoSQL and all that, with all the data that you're getting now with text, you might want to index a description. So here I have an index, a description of RCHAR 200. To make that an index, that's a lot of memory to take up if I've got a very big table. So I may not want to read that whole index. If I could get to that index and use that index with a like and just put so many characters, because I know it's unique, then I can actually do a partial index. And so here I actually alter table class, add index, and give it a description of 3 instead of 200. Now, of course, you have to know that you can only access the first 3 characters when you do that, but it'll actually come up and tell you that it used a description index and it did a partial index scan. So just another technique that you could use if you had to. In MySQL 5.7.7, you can do a virtual column. And for your Oracle DBAs, it's kind of equivalent to a function index. Not necessarily, but if you have some column that you want to do some math on and you don't want to do it a bazillion times as you're creating the query, as it's running, you can actually create a virtual column. And maybe you're going to actually want to query on that virtual column. Well, what you can do is you can create a virtual column. It doesn't store it in the table. You turn around and create an index on that virtual column. It'll store it in the index. Much lighter weight to actually maintain an index versus the entire table. So here is how you do that. Basically, I alter table, and I used a different table, v-registration. And I was thinking, well, for my sign-up day of the week, I want to know what, Monday, Friday, when's the best day to sign up. Well, if you use a function around sign-up date, it's going to turn off any index, right? So what I did was I altered table registration, add column, and that's my virtual column of sign-up day of week. And then the keywords here is generate always as, and then I give it what I want to do with it, with day of week, puts around sign up date, and I say virtual. And then I turn around and I create an index. And I use the same names, but sign up day of the week on registration, sign up day of the week. And so then basically I can, I'm actually using that index there. So here I'm actually using it in a group by. I'm saying, okay, so give me sign up date and a count, group by sign up date of week, having count less than 10,000. And you can see it's going to tell me that and do that. So any questions on that? No. Oh, the index is the virtual column will be persisted in the index. Okay. It'll be there, but you won't see it in the table. Okay. Other types of indexes that go beyond this presentation are full text, spatial, and hash for memory engine. I just want to list them here because if you've got those type of configurations, just realize there's more things you can look at. Oops, I didn't mean to get out of that, sorry. Okay, so now that brings us to step number 10, and this is kind of my rinse and repeat step. You're going to rerun, you're going to check your runtime details, compare your metrics, look at your rows, examine rows sent, and then if you have an improvement, just keep trying. So I thought, okay, I got a lot of throughput. I could have stopped back, but I thought, well, let's see what a covering index would do. So I added this covering index, CIDX registration, on my class ID, my send update, and my cancel flag. And the reason why I chose that order is because class ID was a foreign key, sign update was very specific, canceled was less, and there was data skew. So even in a composite key, you have to be careful about the order in which you're doing it in MySQL. So I added that, and you can see it's used it. And instead of, if you remember, we did 2 rows, and then we did 38 rows. I think it was 38 or 39 in my last one. So why one more? And then we got 1 row again. Well, did I improve it? Well, I didn't. Things went way out of whack. And the reason why is because MySQL cannot use B-tree indexes with a range. You think about a B-tree index, it's got to follow a path. If you've got a range, then it's like, I can do this. So if you noticed, in here it says, I'm going to use that index, but I can only use the first part. So it went back and actually went to the registration table with that. And you can see here, executions went up, but my time went way up. I had like 73 milliseconds, and now it's up to 320. Rows examined went way back up there too. Of course, I had more throughput, but it didn't work the way I wanted it to. So in lesson number 2 or whatever, just make sure that if you put a covering index, is that it's interpreting it correct, because otherwise you're just spending more cycles maintaining that covering index when it's not using it. Okay, so step number 11, monitor your tuning results. And this is where you just keep, iterating over it. If you tune it, the one thing about this step, and the reason why I put it in here as a separate step, brag about yourself, because no one else will. But if you really tune it, go, actually be proud of yourself, go show it, and actually keep tuning, because it's an iterative process. If you tune one SQL, sometimes another SQL will appear, because whatever you've done to this one might have impacted that one. Okay, so did we improve it with that covering index? And no, we didn't. No improvement. You can see when I added it, and actually, let's see, 309 milliseconds, all the weight. So it didn't improve it at all. So step number 12, this is my favorite step. This is where I usually find most of my problems, is engineer out the stupid. You look for performance inhibitors. Please don't do row-by-row processing or put it in a cursor. Please try not to do that, because relational databases like set processing. They like to work on sets of things. Look at parallel query. You know, it's not always bad, but in an OLTP environment, sometimes you're just robbing Peter to pay Paul. You are, because you're using more processes for one query, and everybody else has to wait. Alex actually has a nice little article. You can link to that about parallel queries, because they can improve performance in some scenarios. Avoid hard-coded hints. If you see a query with hard-coded hints, make sure it's still valid. You know, data grows, workloads change, and hard-coded hints are hard to change once they get in production, unless you develop in production, but hopefully not. Nested views. Try not to use nested views, and try to state your subqueries in the join, in the main join if you can.